So hey everyone and welcome to Physicam Academy. I hope all you doing good. So today lecture is the topic from advanced quantum mechanics, that is our harmonic oscillator. And you know harmonic oscillator is very important for MSc student, for IIT JM, for NET, for GATE. So if you preparing for any kind of exam, ठीक है, in which physics is your major subject, this topic is one of the most important. If you understood it, if you know how, see, whenever we discussing these kind of potential, I told you either it is one dimensional particle in a box, infinite potential well, and a finite potential well, whatever it is, I told you the most important thing is that we have to find out the energy of the particle, okay, in a particular state, and then we have to find out the wave function for the particle in the different states. Okay, these are the two major concept, two major outcome from these potential. So see, harmonic oscillator is one of the most important type of potential problem we encounter in quantum mechanics. It is behave just like the classical simple harmonic oscillator. We know, we studied the simple harmonic oscillator in classical mechanics. So the potential form remains same, but most of the potential in quantum mechanics, like nucleus potential and so many other potential, we treat as harmonic potential. So it is one of the known and very broadly used potential in quantum mechanics. So see, let's say we have a particle, and this particle is trapped in a kind of potential. Let's say here our particle is trapped. So there is different state, n equal to 1, n equal to 2, n equal to 3, c, n equal to 1, n equal to 2, n equal to 3. So our particle inside this potential, you know, this potential is kind of this type of behavior. Okay, you say behavior, this is the stable point here. So let's say there is a particle. So in this case, you see here inside, from here to here, the energy, total energy of particle is greater than potential. Outside this boundary, the potential is greater than here. If you go outside here, let's say here outside, what happened now, the potential is greater than energy. So the wave function is only, or the particle is only found within this region only. Okay, within this region. Are you getting? No particle outside this potential. So the potential half kx square, that is, you can say half m omega square kind of. From here, you know, the Hamiltonian operator is a sum of kinetic energy plus potential energy. So I just put here, just multiply with h cut omega both side. So now what we get, just try to understood what we getting from here. We get a very special result out here. We get 1 upon, let's say we writing it 2m h cut omega, I'm just putting it whole square p mod square plus m omega upon h cut root whole square x dot square. ठीक है, I hope है ना you understood it. So now we have to introduce two type of operator. One is a is called your lowering operator. So why it is called lowering operator? Because it lower the state of a particle. Okay, if you apply this is in nth state, then the nth state become, when you apply this operator on nth state, the state become m minus 1. Okay, when it operate on that particular state. So a equal to, what we write, under root m omega upon h cut. ठीक है, 2 h cut, obviously 2 is missed here, 2 h cut, और x mod है ना, x that is operator, sign of operator x square. Okay, plus I times of p operator, that is in, है ना, you've seen here p operator, p square operator obviously there, upon under root 2 m h cut, 2 h cut, here see 2 m h cut, m also there, omega. Okay, so this is x only, this is the value of h upon h cut omega na. So we have to operate a, है ना, and then we have to operate a dagger. So when I apply a dagger, so what is a dagger? See, a dagger is the complex conjugate of this a lowering operator. This is a dagger, that is called your rising operator. So this is m omega upon 2h cut x. Okay, just try focus here, minus I p operator upon under root 2 m h cut omega. So we got till here without any problem, we understood this. Now when I, so this is our, but this I told you na, this is a lowering operator, and this is, remember it, rising operator. Okay, these are the two operators you need to remember. One is lowering operator here and one is rising operator. So A is a lowering operator, A dagger is a rising operator. How I write? Just see how I'm writing here. Okay, how I putting the values of A and A dagger. This is most important thing for you. So now if you found A dagger A, we have to multiply this with this, that with that. So you got xp minus px here. Okay, so you know the complex the Poisson bracket of xp minus px. It is, this is a Poisson bracket of xp and the its value is ih cut. So when you solve it, what you get, see just multiply this, we get m omega upon 2h cut x square plus this I become है ना, we got p square है ना, 1/2 h cut m omega p square plus I upon 2h cut xp my px है ना, Poisson bracket. So when you solve it, its value is I h cut है ना, so I h cut become h cut cancel out, it is minus half. So A dagger A is equal to, just put the operator sign here also है ना, it's up to you. So we have to take 1 upon h cut omega outside. So what you left with p square by 2m plus half m omega square x square minus 1 by 2. So now from here you see A dagger A, you got the value of A dagger A without an issue, you got the value of this. So from here, this one is your again H, Hamiltonian operator. So we can say Hamiltonian operator H can be written H. How can we write it? A dagger, है ना? A dagger A, not A dagger, plus 1 by 2 here H cut times of omega. Okay, and similarly H can be write as A dagger minus half H cut omega. This is also a pattern. We can write it. So in harmonic oscillator, we can write the Hamiltonian operator in term of lowering and rising operator also. I hope till here there is no problem. You will able to understood, है ना, यहाँ तक समझ में आ गया होगा. Now if you find the Poisson bracket of H and A dagger, okay, or A dagger A, it comes out to be 0. You can put the value and got the answer, and it cancel out and you getting 0 answer. And if you finding out A dagger Poisson bracket, you found, how can you write out A dagger minus A dagger A, and the Poisson bracket of AB is AB minus BA. Okay, so from here if you found it, what you get 1 if you put the complete value. And similarly A dagger A, if you find out the A dagger A, it comes out to be minus 1. Okay, if you found the Poisson bracket of A dagger A, it comes out to be minus of 1. Now let n is a eigenvalue, n is a eigenvalue or eigenstate. We write it, this is your cat bracket of is a eigenfunction, this is a quantum mechanical in Dirac notification. This is a eigenfunction. So if this is eigenfunction and you operate A dagger on this eigenfunction, what happen? You got eigenvalue n. Okay, what you get? You get eigenvalue n like this. So from here also when you apply H on this, okay, you know the value of H is A dagger plus half H cut omega. You can write it down. And so from here when you apply H on this, you got the energy eigenvalue dash, this. So the energy eigenvalue of nth state is how much? You can say when you apply A dagger on this wave function n, you getting the value, if you put this value here, you get n plus half H cut omega. Okay, so you get En equal to n plus half H cut omega. So this is the energy eigenvalue of nth state of a harmonic oscillator. Either way it is n equal to 1, n equal to 2, n equal to 3, n equal to 4, whatever you put, you get the energy eigenvalue for this particular state. Now talk about A and A dagger. So I told you A dagger and A. So this is A dagger. When you apply A dagger on any state, A dagger is your rising operator. So when you apply, you get n plus 1 with something constant. Let's say I'm taking it as C, C. Okay, and when you apply A on nth state, this is a lowering operator. So C dash है ना, it lower the state. So now you know every quantum mechanical wave function is what, normalized wave function. So if you want to find out the value of this term c and c minus, so what you get, c minus is equal to root of n and c is equal to root of n plus 1. Easily you can find out, huh? Let's take a eigen function cat vector of n, then you apply the operator on this, है ना. Let's say just I'm giving you example here. Let's say I'm finding this, okay. Let's say this is a dagger a, on nth state I'm applying, so we get 2c complex conjugate. We don't know the answer of this, so it lower the operator n minus 1, okay. And here again like this. I hope you getting n minus 1 because a dagger you applying on the function, it is a lowering operator, you know. So this here when you apply this function, so you get like this, then equal to c mod square we can put it, okay, without any problem we can put it. So from here n take outside, so n cat bra vector c mod square, so this is become 1, so c is equal to under root of n, okay. C is equal to c minus, sorry, this is c minus now, c minus is under root of n, okay. So here you have to put your wave function is under root n plus 1, okay, n plus 1, and here it is root n minus 1. If you found any difficulty in this lecture anywhere, you just connect with me, okay. I will try to help you there. Now the second thing, how you find out the wave function. The second most important thing is wave function. Wave function for harmonic oscillator. So how you find out, you know your operator, okay, that is your lowering operator. It is how you writing m omega upon 2h cut x plus I, and you just put the value of what you just put the value of p here, p equal to minus I h cut omega in term of operator 2h cut m omega. This is enough, and let we applying this on a wave function psi naught. So when we apply this on a wave function psi naught, it give you 0 value, okay. It is the ground is 0, we applying it on the 0th state, okay. So you know what you get 0 obviously, है ना. 0 cannot be reduced to minus ना, so 0 the lowering operator, है ना, n is 0, so you get under root of 0, so the wave function that side becomes 0. Now what you do, just try to solve it out, you got your answer. So h cut dy dx of psi naught, okay, whatever is your psi naught x in wave quantum mechanics, or in Dirac notification you can say cat of psi naught, okay, upon 2 h cut m omega, this will be fine, minus under root m omega upon 2 h cut, this is our operator x psi naught. X is a multiplicative operator, this I think you know it very well, okay. Some of you know, some maybe by dx. Just try to solve it out, minus m omega, you just cross it, multiply upon h cut x psi naught x, integrate both side, okay. When you do an indefinite integration, you get ln of psi naught is equal to minus m omega upon h cut, okay. There are two operators, it become x square by 2 plus log of c. With respect to dx we will integrating it, okay, do not bother about. I hope till here there is no issue, no problem, you had understood all the things in a very detailed way, okay. This thing, is it clear now? So we just operate it, multiply it, solve it. So x is operator, so it become with respect to x, when you integrate it, it become x square by 2 log of c. So here from here log this log a minus b log a upon b, so a equal to this minus, it become e to the power exponential minus m omega upon 2h cut x square. This is our quantum mechanical wave function. So now if you integrate it, minus infinity to plus infinity, you know psi dagger dx should be equal to 1, normalization condition, है ना. normalization condition. Every quantum mechanical wave function should follow this normalization condition. So when you apply, when you integrate it, it's a little bit difficult integration. You get the value of a, this constant a. Okay, I'm just putting it directly. You just have to integrate it. N factorial root of pi, n factorial root of pi, and with this h n alpha x. So what is this? This is a h n alpha x is a operator, again Hermitian polynomial है ना, Hermite polynomial. It is a Hermite polynomial. Okay, HNX. So you can study Hermite polynomial in mathematical physics. When we start mathematical physics, we definitely study Hermite polynomial. So I feel this lecture is a little bit difficult if you see it, and you can see the wave function also. In ground state, you see your wave function is like this. Here ground state is starting from 0 na, n equal to 0. Your wave function is something like this. Okay, in first excited state n equal to 1, your wave function is looks like this, like this, like this, like this. Okay, so different scenarios are there. So it is same as one dimensional particle in a box. You need to remember the energy eigenvalue. This is one dimensional harmonic oscillator. We're not talking about the three dimensional harmonic oscillator. Later on, when we move on after that, obviously we just going to the three dimensional potential problem, that is particle in three dimensional box. Then we study the three dimensional harmonic oscillator. Then we will study WKB approximation and perturbation. We will start the energy eigenvalue degeneracy we will study. Okay, so these are the topic uh, we going to study later on. So till here, thank you, bye bye, stay tuned, and make sure you should like, share and subscribe this video channel.